How's it going? I would say welcome back, but this is the first video I've ever done, so welcome to the inaugural video, I guess. So what we're going to be doing today is an EOC problem that I assigned to my students for force of friction, and it looks like this. It's going to be question 1 of this worksheet. So it reads, a 3 kilogram wooden block is resting on a wooden table, an applied force of 10 newtons is acting to the right. 3 parts. Part A is draw a free body diagram. Part B is to determine the normal force. And part C is to calculate the maximum static friction force and compare it to that normal force. And then, is the block moving or should it be moving? So let's go into it, and let's start with our free body diagram. Notice that this says the block is resting, and since the block is resting, it means it has to be in equilibrium, which means all the forces on it have to cancel out or have to add up to 0. So let's show that in our free body diagram. So we'll do it up here on the right side, on the left side. So this will be part A. So part A is a free body diagram, so let's draw a little box. And we could start by drawing forces on this box, and we could start with the force due to gravity, or the weight of the box, and that is going directly downwards. Always points directly downwards. And the weight we know as force due to gravity, F sub g. In order to cancel that out, we need a normal force. That normal force always points perpendicular to the surface that is causing that normal force, and it's always a push away from that surface. So it will be directly upwards. So it'll look a little something like that. Now we have an applied force of 10 newtons acting to the right, and so the applied force will be acting to the right, like this. We'll label that F sub A. And then we have a frictional force. Now this frictional force has to be equal to the applied force in order for it to be at rest in equilibrium, so it'll be pointed to the left. That'll be force of friction. Now these don't have to be perfect, like I don't need to measure this line and this line per se, but approximately the same length, the same magnitude is definitely required. So that's it. That's all you need for part A. So let's move on to part B, which is determine the normal force acting on the block. Now if we're determining the normal force acting on the block, then we could say, well, let's start writing down some numbers. Let's start making our knowns list. So no, 3 kilograms is the mass, and we know this as the mass because of its unit, kilograms. We measure mass in kilograms, we measure weight in newtons. So 3 kilograms is our mass, and we have an applied force of 10 newtons. So let's just throw that down there and see what we can do to find the normal force. So this will be part B, so we know the mass is 3 kilograms, and the force applied 10 newtons. Now, I always start with writing my Newton's second law, and so that is going to be the sum of all forces equals mass times acceleration. Now, since we're working on normal force, it is important to note that we really are only working on the y direction here. We cannot mix our x and y directions, and so since it is in the y direction, let's just focus on the y direction. So we're going to write F sub y equals ma sub y, since the net force and the acceleration have to be in the same direction. So we simplify the left side of the equation first, and so let's list all the forces that we have in the y direction, making sure we keep track of which way they're pointing and which sign they should be. So anything that's up is positive, anything that's down is negative. So right now we have Fn pointed upwards, and we have F sub g pointed downwards, and so Fn is going to be positive minus F sub g, and that's going to equal may, or ma sub y. So you should notice that, hey Mr. P, you said this box is at rest, so if it's at rest we should have no acceleration on it. That's absolutely true. So this whole term, if acceleration is 0, goes to 0. And then we can add fg over and say f sub n is equal to f sub g. Now this is a mathematical representation of something we already said. We said that the forces have to cancel out. In order for them to cancel out, they have to be equal, and here's our mathematical representation of that. So, you might think, okay, well if I know what Fg is, then I can find Fn, but I don't know what Fg is. But I do know what mass is. And if I know what the mass is, I can use my weight formula, F sub g equals mg, to find that force due to gravity, to find that weight. So here we have F sub g is equal to my 3 kilograms times, well, it's little g and it's on Earth, so it's 9.81 meters per second squared. And then if we multiply those two out, we get 29.43 newtons. And this is newtons, kilograms times meter per second squared, and it's also a force, so it's the easiest way to notice. That is definitely newtons, and so if that's 29.43, well then F sub n, the normal force, is also 29.43 newtons. So there's part B. There we go. Hardest part of that is to first figure out the left side of this formula, and then recognizing that we don't know the weight, but we do know the mass, and therefore we can find the weight. So now let's go to part C. And part C says, calculate the maximum static friction force and compare it to the normal force, and then should the block be in motion. So we are looking for static friction. So we're gonna F-I-C-T-I-O-N spelling. We're going to find the force of friction, which is equal to mu times force normal. Now this box is not in motion, so we could say that this is static coefficient of friction, u sub s force normal. And so you might think to yourself, Mr. P, how do we know the coefficient of friction? You should think to yourself, well, this is not something that I should be expected to know, and you're not supposed to be expected to know it. You do have your reference table. So let's pull up that reference table. It's right here on the right, and it's actually on this front page of the reference table, which is kind of nice as well. So, whoops. So it's right here, right above my head. And so we have approximate coefficients of friction, both to the kinetic and static. We are looking for a wooden block on a wooden desk, or wooden table. So it's wood on wood right here, and the static for wood on wood is 0.42. So let's list that in our notes. Let's write mu static equals 0.42. Now this does not have units to it. It's one of the only things in our curriculum that does not have units to it because it is a ratio. So if we're finding the force of friction, we're going to set it equal to 0.42 times, well, my force normal I already found, 29.43 newtons. Now let's find the force of friction, which comes out to 12.4 newtons. The math of this problem is all done now. Now we have to go into the conceptual just a little bit, because we have to ask ourselves, should the block be in motion? Now, you might think to yourself, well, Mr. P, that 12.42, that's greater than the force that's being applied. But here's the thing. You cannot push something or apply a force on something that is at rest and it start to move based off of the static friction force. There's no way you push it forward, but the static frictional force is so large that it starts accelerating backwards. The static friction force will not cause an unbalanced force acting on your object. Now the kinetic friction force certainly can, and that would cause an object to decelerate essentially. And so what we're looking at here is the static friction force will match whatever you apply to that box up until my maximum, which we just found is 12.4. So if you push 10, the static force of friction will also push 10. You push 11, it'll also push 11. But the instant you go above 12.4, that is when the box starts moving. And once the box starts moving, there's a whole bunch of other stuff going on, with the coefficient of kinetic friction being lower than the coefficient of static friction. And so we'll get into that a little bit, but just recognize that the actual box currently, while it's at rest, if you're pushing on at 10, has 10 newtons backwards of the force of static friction. It cannot be greater than the force that you apply. So that is question 1 of the EOC homework. So I hope you enjoyed it for a first video, and hopefully there's no hiccups or bumps when I edit this out, but thank you for watching and stay awesome.